Last week, I was sitting in a sleek, glass-walled office in a tech hub, talking to a venture capitalist who was vibrating with excitement. He spent 20 minutes showing me a series of charts on his tablet, all related to the exponential growth of AI software and the dematerialization of the modern economy. He kept using the word weightless. To him, the future was a clean, digital frontier where value is created out of thin air, and physical constraints are a relic of the 20th century. His focus was entirely on the invisible layer of the world. But then, the power flickered. It was just a momentary dip. But for a second, the hum of the climate control died, and his tablet screen went dark. He looked at the wall with the expression of genuine annoyance, as if the physical world had just insulted him. He didn't see the irony. He went right back to his weightless narrative, but it made me realize how profound the disconnect has become. We are currently living in an economy that allocates attention before it allocates capital, and right now, all the attention is focused on the glow of the screen. Hardly anyone is looking at what's behind the wall. What was fascinating was when I asked him where he thought the power for his infinite AI models was actually coming from. He gestured vaguely toward the cloud. He didn't want to talk about the 83 kilograms of copper in every EV in the street outside, or the 3 tons of metal required for every megawatt of renewable energy being plugged into the grid. He certainly didn't want to hear about the 15-day maritime voyages or the 3,000-kilometer transport routes required to get raw materials to a smelter. To him, those were slow problems. That's the danger of the attention economy. Markets don't price reality evenly. They price what they are looking at. We've built a massive narrative around a digital revolution while ignoring the physical foundation that has to support it. But here's the thing about physical systems. They don't care about narratives. While the market is distracted by the speed of software, the physical supply chain is hitting a structural bottleneck. When the attention finally shifts from the invisible to the essential, the price adjustment won't be a gradual trend. It will be a violent collision between narrative and necessity.
Yeah, that violent collision is basically what we're already starting to see under the surface. I mean, the physical infrastructure of the whole global economic system is, it's currently buckling right now under the immense weight of this supposedly weightless technology you just described.
Right.
If you look closely at the operational data, the digital ambitions of the modern economy are just vastly outpacing the physical Earth's geological capacity and its logistical capacity too, honestly. We are entering this era defined entirely by hard, unyielding physical limits.
Which perfectly sets up our exact mission for today. Because for this deep dive, we are going to really examine the unseen physical anatomy of the digital revolution.
Exactly, the stuff nobody wants to look at.
Right. Specifically, we want to explore this modern rush for copper, which people are calling red gold now. We're going to map out from you all these severe systemic bottlenecks that are currently masking what is mathematically a structural deficit.
A massive deficit, yeah.
So this is an exploration of that impending economic collision between high-tech, artificial intelligence-driven ambitions and the hard limitations of the physical world. It's essentially the invisible crisis of our time.
Yes, I mean, copper has been the foundation of electrification since, the 1880s?
Yeah, around when direct current networks first lit up urban centers.
Right. But the strain that's currently being placed on this connective artery, the metal linking our physical machinery, our digital intelligence, and our energy grids, it's entirely unprecedented. We've never seen a demand shock quite like this.
So to really understand this, let's step out of the abstract for a minute and travel somewhere highly physical. I want to take you, the listener, to Ashburn, Virginia.
Data center alley.
Exactly. Ashburn is located in Loudoun County, which is essentially the beating heart of the global internet. I want to picture a man named Elias. He's an electrical contractor, and he's standing inside the skeletal, heavy steel frame of a premier, state-of-the-art AI data center that's currently under construction.
Okay, for that.
So all around him, the architectural plans are dominated by the language of the modern economy. Right. They're talking about closed-loop liquid cooling systems, high-density H100 GPU clusters, neural latency optimization.
Which are the exact buzzwords that venture capital is aggressively funding right now to win the AI race. They hear neural latency and they just write a check.
Right. But Elias's reality is entirely disconnected from those buzzwords. His daily existence on that job site is measured in millimeters, torque specifications, and metric tons.
Yeah, the heavy stuff.
Exactly. So he's staring at this massive, highly specialized step-down power transformer sitting idly in the corner of a vast concrete data hall. It is a multi-million-dollar piece of equipment, and it is completely paralyzed.
Because it can't be plugged in.
Yes. because it is missing the high-gauge copper busbars required to physically connect it to the regional electrical grid. Wall Street is pouring billions into semiconductor equities, but Elias is spending his nights cold-calling industrial scrapyards. He's calling secondary metal suppliers. His hands permanently carry that distinct metallic scent of oxidized copper.
Which is such a perfect encapsulation of the disparity between software development and hardware reality right now.
It's a profound cognitive dissonance. He's standing in a facility meticulously engineered to accelerate digital computation at warp speed. Yet the entire multi-billion-dollar project is grounded by the stubborn physical reality of a base metal.
The attention economy funded the brain, but it completely neglected to construct the nervous system.
Yes. He feels the weight of this invisible crisis every single day. That gap between the brilliance of software engineering and the silent, unyielding shortage of the metal required to actually turn those servers on.
And to understand the physics behind Elias's supply chain nightmare, you really have to look at the extreme density of what is actually being built in Ashburn.
What do you mean by density in this context?
Well, we have experienced this explosive architectural shift from traditional cloud computing facilities to these new generative AI architectures. The power density requirements are fundamentally different. I mean, a modern AI-specific data center demands up to 47 metric tons of copper for every single megawatt of capacity.
Wait, let's establish a baseline for that for a second. 47 metric tons per megawatt. How did that mathematically compare to the older data centers we were building, say, just 5 years ago for standard cloud storage?
It is nearly double the requirement of those legacy facilities.
Double. Just guys.
And to understand why, we have to look at the physics of electrical resistance. Next-generation GPU architectures, like the Blackwell and Rubin series, they possess extreme thermal and electrical densities. Standard alternating current systems just cannot handle them efficiently. They require specialized 800-volt direct current power systems.
Okay, but why does an 800-volt DC system demand so much more physical mass of copper? Like, why can't you just use standard heavy-duty industrial wiring? I mean, we wire industrial plants all the time.
It basically comes down to joule heating.
Okay.
So the formula for electrical power loss is current squared multiplied by resistance. When you are pushing thousands of amps to a highly concentrated cluster of processing units, standard insulated wiring just fails.
Just can't take the load.
Exactly. The resistance within a normal wire generates so much heat that you experience catastrophic energy loss. And worse, the insulation simply melts, which poses a severe fire hazard. So to solve this, you have to eliminate standard wiring entirely. You have to use what are called bus bars.
Okay, describe what a bus bar physically looks like for someone who hasn't spent time inside an industrial power room.
Right, so imagine a solid rectangular slab of pure copper. It's often an inch thick and several inches wide, and it runs suspended across the ceiling or under the floorboards of the facility.
Just a solid block of metal.
Yeah, a massive solid bar. Because copper has one of the highest electrical conductivities of any non-precious metal, these massive bars allow extreme electrical loads to flow with minimal resistance.
Which means minimal heat generation.
But the trade-off is that they are incredibly heavy, highly expensive, and physically unyielding. You cannot just bend them around corners easily like a wire.
Right, you can't just spool it out.
No, they have to be precision machined and bolted together with exacting torque. And for AI data centers, they are absolutely non-negotiable. You literally cannot run the models without them.
To put a specific number on the scale of this physical deployment for you guys listening, consider a single facility built recently in Chicago. Just during the construction phase, purely to wire the internal infrastructure, that one single building consumed 2,177 tons of copper.
Which is just staggering for one building.
Yeah.
And if you extrapolate that single building to the macroeconomic trend, the trajectory becomes genuinely alarming. So in 2023, data center copper demand was approximately 467,000 tons globally. By 2030, that specific demand vector is projected to surge by 114%, reaching 1 million tons annually. In the United States alone, data centers are projected to leap from consuming roughly 5% of total grid electricity today to as much as 14% by 2030.
So this invisible demand is just violently colliding with the physical market. I mean, we saw the result of this demand shock when copper prices hit historic heights, peaking at, $14,527 per metric ton in early 2026.
Yeah, that was the peak.
And it has stabilized around $13,850 recently. But that premium is still permanently altering the landscape.
Well, and the danger of this price environment is exacerbated by the specific nature of the buyers in this space. Hyperscalers, the massive technology corporations building these AI models, they operate under a completely unique set of economic constraints.
So,
even at record high commodity prices, the cost of copper represents less than 1% of the total capital expenditure of a multi-billion-dollar AI data center.
okay, so if I am a tech giant allocating $3 billion for a massive GPU cluster and all the surrounding liquid cooling infrastructure, spending an extra $50 million on copper bus bars is essentially a rounding error to me.
It's not just a rounding error, it is viewed as a mandatory insurance policy. Because the capital cost is comparatively negligible against the total project, these corporations are completely price insensitive.
Meaning they don't care what the copper costs?
They do not care. They will pay whatever the physical market demands to secure their supply and maintain their deployment schedules. The opportunity cost of delaying an AI rollout by 6 months due to a lack of bus bars is exponentially higher than paying a 50% premium on raw copper.
It's like the technology sector has engineered a massive state-of-the-art engine for a supercar, right? They poured hundreds of billions into the aerodynamic chassis, the onboard software, the precision machine cylinders.
Yeah, the glamorous stuff.
But they completely neglected to design a fuel line capable of actually delivering combustible fuel to the engine. And now that they realize the oversight, they are totally willing to pay $10,000 a foot for a reinforced hose just so they can turn the ignition.
And that structural reality creates a severe systemic danger. We are witnessing the solidification of a two-tier commodity market.
A two-tier market.
So in the top tier, you have the hyperscalers who can effortlessly absorb any price shock. They just write the check. In the bottom tier, you have traditional industrial sectors, civil construction, legacy manufacturing, and most critically, renewable energy infrastructure that operate on razor-thin margins.
Right.
In a physically constrained market where there isn't enough copper to go around, the price-insensitive buyers effectively crowd out the essential physical economy.
Okay, that perfectly transitions us to the collateral damage of this dynamic.
Yeah.
Because it's not just happening in a vacuum. I want to shift our focus geographically from those sterile, climate-controlled environments of ash burn to the gritty, heavy industrial logistics layer. Picture a woman named Sarah. She is a logistics coordinator for a major North American copper refiner. And she is standing in the freezing rain, surveying the rusted, oil-stained tracks of a rail yard on the outskirts of Sudbury, Ontario.
Oh, Sudbury. Yeah, that's a historic mining basin. They deal with the raw, heavy realities of extraction and transport every single day.
And inside corporate boardrooms, Sarah constantly hears the grand political rhetoric about the green transition, right? The patriotic necessity of building domestic electric vehicle supply chains. But her daily boots-on-the-ground reality is a brutal war against physical friction and systemic inertia.
What's she dealing with exactly?
Well, currently, she is tracking a specific shipment of refined copper cathode. These are flat, heavy plates of 99.99% pure copper, and they are destined for a massive, newly constructed battery plant down in Michigan.
Okay.
But the shipment is hopelessly stalled. It is sitting idle on a siding, trapped behind a massive backlog of agricultural grain and timber. And it's entirely hampered by a sheer physical lack of specialized flatbed rail cars.
So the physical transport infrastructure is completely failing the mandated timeline of the energy transition.
She looks at her terminal, and she reads market indicators published by financial analysts in New York who claim the supply chain is stable simply because the spot price hasn't spiked further today.
Right. They look at a screen and think everything is fine.
But with her own eyes, standing in the rain, she sees the fraying edges of an aging network. The political mandates of 2030 are violently colliding with the 1950s logistics reality. To the financial analysts, this delay is just a latency metric on a spreadsheet.
Yeah.
But to Sarah, it is the smell of diesel exhaust. It's the sheer physical weight of the metal. And it's the deafening silence of a stalled freight train, which guarantees that the renewable wave is hitting a structural wall.
And what Sarah is managing there, that is the physical manifestation of what we call the green squeeze.
The green squeeze?
Yeah, the very technology that the market believes will optimize our future energy grid, artificial intelligence, is actively stalling the deployment of carbon-free energy generation. Both sectors are fighting a zero-sum battle over the exact same physical wire.
Let's break down the mechanics of this green squeeze for everyone. Yeah. Why exactly is the renewable transition so painfully vulnerable to a copper bottleneck? Like, why do they need so much of it?
Well, the transition from fossil fuels to renewable generation and electrification is inherently copper intensive because of how electricity is generated and stored.
Okay, let's look at EVs.
A standard internal combustion engine vehicle, a gas car, requires roughly 20 to 25 kilograms of copper, mostly just for the wiring harness and small auxiliary motors.
Right.
But an electric vehicle, that requires roughly 83 kilograms of copper.
83 kilograms. That is nearly a 4-fold increase per vehicle. What physically demands that much copper in an EV?
It's the core mechanism of propulsion. The traction motor of an electric vehicle relies on massive electromagnetic fields, and those are generated by dense coils of copper wire wrapped around the stator and rotor.
You can't just bypass.
Well, you cannot miniaturize or optimize away the laws of electromagnetism. You need the physical mass of the copper to generate the magnetic flux required to move a 2-ton vehicle. And when we look at power generation, the multiplier is even more extreme. A single 1 gigawatt offshore wind farm demands nearly 2,900 tons of copper.
2,900 tons for the single wind farm installation. And I'm guessing renewable project developers do not have the infinite price-insensitive balance sheets of the tech hyperscalers.
They absolutely do not, because the hyperscalers are driving up the marginal cost of copper and basically locking up physical supply contracts. Renewable developers are facing an existential financial crisis. The physical consequences are visible across the entire supply chain right now.
Give me an example of the fallout.
Well, we are currently tracking lead times for grid-scale electrical transformers that stretch past 40 months.
40 months. Wait, so if you need a transformer to connect your brand new wind farm to the grid, you are waiting over 3.5 years just for the hardware to arrive.
Yes. It makes aggressive green transition timelines mathematically impossible. And consequently, project developers are increasingly halting what we call final investment decisions, or FIDs, on major wind and solar installations.
Because the math doesn't work anymore.
Exactly. When they recalculate their financial models using current raw material costs and these 40-month delays, the economics no longer pencil out. The return on investment completely collapses. Furthermore, smaller EV startups, the ones facing severe cash burn right now, are attempting to substitute inferior aluminum for copper in non-critical wiring harnesses just to survive the margin compression.
I really want to focus on that substitution for a moment. If aluminum conducts electricity and is, vastly cheaper and lighter than copper, why is substituting it considered inferior or dangerous?
It's a physics problem. Aluminum possesses about 60% of the electrical conductivity of copper. Therefore, to carry the exact same electrical current, an aluminum wire must be significantly thicker.
Which takes up more space.
Which requires more spatial volume. And that is a massive penalty in automotive engineering where space is incredibly tight. But more critically, aluminum has a higher coefficient of thermal expansion.
Meaning it swells up when it gets hot.
Right. When the wire heats up under electrical load while driving and then cools down when parked, it expands and contracts significantly more than copper does. Yeah, over time, this phenomenon, which engineers call creep, causes mechanical connections at the terminals to loosen. And loose electrical connections create micro-arcing.
Micro-arcing, like tiny sparks.
Yes, tiny electrical arcs jumping across the gap, which generates intense localized heat, eventually melting the surrounding plastics and triggering catastrophic vehicle fires. Physics fundamentally punishes the substitution. You just can't cheat it.
There is a deep, profound irony here. The dominant narrative out there is that society is saving the planet through green energy electrification. But that narrative is being quietly and ruthlessly derailed by the parallel narrative of creating artificial superintelligence.
Right.
We are mathematically starving the very physical grid that AI completely relies upon to function.
It's a paradox. And this specific bottleneck is a subcomponent of a broader macroeconomic trend that we call the electrification of everything.
Right, because everything is plugging in.
Exactly. Global electricity demand is projected to jump by 50% by 2040. To physically transmit that power, the global electrical grid must expand by 53% in the same time frame.
That's a staggering amount of infrastructure.
Estimates suggest that grid expansion alone will require 427 million tons of copper by mid-century. But the mechanics of the two-tier market dictate that capital-rich AI infrastructure acquires the copper first, leaving the foundational grid totally starved of the physical materials required to expand.
This scenario just feels mathematically impossible to resolve. And it forces us to look at the total global demand picture. Because, AI data centers and the green transition are massive demand shocks, but they aren't operating in a vacuum. There are actually 4 distinct massive vectors of demand occurring simultaneously right now. And together, they're driving a projected 50% increase in global copper requirements, going from 28 million tons today to 42 million tons by 2040. Let's systematically break those 4 vectors down for everyone.
Absolutely. So the first vector is what commodity analysts historically refer to as Dr. Copper.
Dr. Copper.
Yeah, it represents core macroeconomic demand. For decades, copper has been the ultimate diagnostic indicator for the health of the global economy. If housing starts, automotive manufacturing, and consumer appliance production were rising, copper demand rose in lockstep.
Right, it takes the temperature of the economy.
Exactly. Today, this vector remains the largest foundational pillar, and it is expanding aggressively due to the rapid modernization of the developing world.
Because as global living standards rise, the demand for basic electrical amenities just skyrockets. And the projections here are staggering. Demographic and economic models indicate that 2 billion new air conditioning units will be installed globally by 2040.
2 billion.
Primarily in emerging economies facing rising temperatures.
And think about what that means physically. Every single one of those 2 billion air conditioners requires copper heat exchangers, copper tubing for the refrigerant lines, and dense copper windings inside the compressor motors. It is a massive, decentralized physical drain on global supply.
And compounding that baseline demand is the geopolitical shift toward reshoring manufacturing. As the United States and Europe try to pull critical supply chains out of Asia to rebuild their domestic industrial bases, constructing those massive new automated factories requires thousands of miles of heavy-duty copper conduit.
Right, robotics wiring, industrial power distribution systems. It all needs copper.
So that's vector 1. What about the second one?
The second vector is the energy transition and addition that we previously detailed. But beyond just electric vehicles, we are witnessing the structural rewiring of the entire planet.
Give us a scale on that.
China is expanding its national power grid at a rate of 3.2% annually. They're building massive, ultra-high voltage direct current transmission lines across the entire country. India's grid is growing at 4.2% annually. This is the sheer physical infrastructure required to move electricity from remote, renewable generation sites down to dense urban load centers.
Okay, and the third vector, which is acting as an unprecedented accelerant on the entire system, is the AI and data center build-out, which we've thoroughly mapped out already.
Yes.
But the fourth vector is one that traditional technology analysts almost entirely ignore, and that is defense modernization.
Huge. Geopolitical tensions are structurally shifting the nature of military conflict. We are witnessing the rapid electrification of the battlefield. NATO countries are facing intense internal and external pressure to increase defense spending closer to 5% of their GDP.
And allocating capital to modern defense does not mean casting steel tank treads or machining lead artillery shells anymore.
Modern deterrence and warfare are entirely dependent on advanced electronics and automated telemetry. We are looking at the mass production of drone swarms, precision-guided munitions packed with complex internal sensors, and massive, highly secure EMP-shielded telecommunication arrays.
Which are all heavily reliant on copper.
And the capital deployed for these systems is considered completely inelastic. Sovereign governments will pay whatever premium is required to secure supply chains for national security, perfectly mirroring the price insensitivity of the tech hyperscalers we talked about.
Right. A government building a missile defense system doesn't care if copper is $20,000 a ton.
Exactly. Consequently, defense-driven copper demand is projected to triple by 2040.
Okay, so when you aggregate those 4 vectors, baseline modernization, the green grid transition, AI infrastructure, and the electrification of defense, we are staring at a requirement for an additional 14 million tons of copper demand by 2040.
Yes, 14 million additional tons.
That forces us to look at the supply side. What is the physical reality of global mining operations against this 14 million ton wall of demand? Like, where is it coming from?
Well, the supply reality is defined by a concept known in the industry as the cliff. It's not. Against this massive demand surge, primary mine supply globally is completely stagnant. Output from every existing, currently operating mine on Earth is mathematically modeled to peak at approximately 27 million tons in 2030.
Okay.
And after that peak, production will steadily and inevitably decline to roughly 22 million tons by 2040. As those existing geological assets are naturally depleted, the ore just runs out.
Okay, if you do the math on that, it is a chilling realization. If total global demand accelerates to 42 million tons and the supply from existing operating mines drops to 22 million tons, we are facing a structural physical deficit of 10 million tons by 2040.
Correct. Even when models factor in the new mining projects that are currently classified as highly probable to reach commercial production, we are still looking at a catastrophic shortfall. The world will be roughly 20% short of the copper strictly required to meet global net zero goals.
20%.
To understand the severity of that, consider that the largest historical deficit the copper market experienced between 1994 and 2020 was a mere 2.5%.
Wow.
A 20% physical shortfall will completely fracture global supply chains.
Whenever this deficit is brought up in policy discussions, the immediate counter-argument is always recycling, right? People assume we can simply execute massive urban mining campaigns, just melt down discarded electronics, old wiring, and scrapped vehicles to close the gap.
It is a persistent and incredibly dangerous myth.
Why is it a myth?
I mean, secondary supply through recycling is critically important, yes, but it's physically and mathematically impossible to recycle our way out of a structural deficit of this magnitude. Even with the most aggressive, heavily subsidized end-of-life recycling programs, secondary supply can only cover roughly 1/3 of the total future supply requirement.
Only a third.
Yeah, you simply cannot generate 14 million tons of new, unprecedented demand and expect to fulfill it by scavenging old wire from demolished buildings. Continuous, expanding primary mine supply, pulling new metal from the earth remains an absolute, non-negotiable necessity.
Which leads to the most obvious fundamental question regarding market mechanics. If the commodity price is hovering near historical highs, right, and future demand is virtually guaranteed by the inelastic balance sheets of tech giants, sovereign militaries, and the global grid, why aren't multinational mining conglomerates just deploying capital and digging more holes right now?
Right, why not just more mines?
Yeah. Why isn't the market naturally balancing itself through a massive boom in new supply? That's what capitalism is supposed to do.
Well, that question cuts to the core dysfunction of the heavy industrial economy. The mining sector is incredibly inelastic. You cannot write a software patch to generate copper.
Right.
The industry is currently trapped in a deep state of operational paralysis, constrained by forces both deep below the ground and high above it.
Let's start with the most shocking metric defining this paralysis. And for me, it's the timeline, the 17-year lag.
This is the defining metric of the impending crisis. Based on global averages, it currently takes 17 years for a new copper project to move from the initial geological discovery of the ore body to the first day of commercial production.
17 years. Okay, let me make sure I'm understanding this. That means if a geologist discovers a massive high-grade copper deposit today, right now in 2026, that specific deposit will not yield a single ounce of usable refined copper until 2043.
Exactly, 2043. And to understand why it takes nearly 2 decades, we must break down the specific below-ground and above-ground friction points.
Okay, let's look at below ground first.
Below ground, the physical geology of the Earth is becoming vastly more difficult to exploit. We have already mined all the easy, shallow, high-grade copper deposits over the last century. Globally, the average ore grade is steadily declining. Decades ago, a standard mining operation might process rock that contained 2% pure copper. Today, new operations are frequently mining rock that is 0.5% copper or even lower.
Let's explain the physical consequences of that grade decline. Because going from 2% to 0.5% doesn't just mean less profit, it means you physically have to extract, transport, crush, and chemically process 4 times the amount of solid rock just to yield the exact same amount of copper you produced 20 years ago.
The physical toll is immense. It means haul trucks. And we're talking massive machines carrying 400 tons of rock per load, burning thousands of gallons of diesel fuel. They must run 4 times as many routes.
Just to break even on output.
It means the massive steel ball mills grinding the rock into powder consume exponentially more electricity and suffer severe mechanical wear. Mines must become vastly larger, significantly deeper, and exponentially more complex from an engineering standpoint. And as operations go deeper, they encounter severe resource constraints, most notably water.
Oh, water. A perfect example of this is the Atacama Desert in Chile, right, which is the world's premier copper-producing region. But it is also one of the driest places on Earth.
It's hyper-arid. And copper processing, specifically the grinding and chemical flotation stages, requires massive volumes of water. Because of severe prolonged droughts and competing demands from local agriculture, the Chilean government is heavily restricting fresh water rights for industrial use.
So how does a mine adapt to having its water supply cut off in the middle of a desert?
They are forced to engineer massive, highly capital-intensive workarounds. The mining industry is currently building enormous reverse osmosis desalination plants on the Pacific coast. They intake seawater, strip out the salt using high-pressure membranes, and then pump that desalinated water through massive steel pipelines hundreds of kilometers inland. And not just inland, they have to push it up 3,000 meters of elevation into the Andes Mountains just to reach the processing facilities.
The physical friction of pushing millions of gallons of water up 3,000 meters of vertical elevation is staggering. The energy penalty alone must just destroy the operational margins.
It drastically increases the sustaining capital intensity required just to keep an existing mine operational, let alone the capital required to permit and construct a brand new one. The Earth is physically resisting extraction. But, the above-ground challenges, the human-engineered friction, are arguably much worse.
Yeah, let's examine those above-ground constraints, starting with the sheer capital requirements.
Because of the declining geological grades and the necessary complex engineering solutions like desalination we just talked about, the global mining industry requires over $210 billion in capital investment by 2035 simply to meet baseline supply projections.
$210 billion.
And to contextualize that figure, it is nearly triple the $76 billion the industry spent over the previous 6 years. Capital expenditures required to bring new supply online in Latin America have surged by 65% just since 2020.
And even if a massive conglomerate actually possesses the billions of dollars required, they immediately run into a paralyzing policy wall.
Absolutely. We are witnessing a global wave of aggressive resource nationalism. Sovereign governments observe high commodity prices and immediately alter their royalty regimes or implement sudden windfall taxes.
Right. They see the high price and want a bigger cut.
Exactly. But this destroys the long-term financial models that mining conglomerates and their institutional investors rely upon to justify a 17-year capital lockup. If the tax rate changes halfway through, the math falls apart.
And then there's the permitting.
Oh, the permitting process is characterized by endless judicial reviews, overlapping environmental impact statements, and intense localized opposition. Right now, there is an estimated 6.4 million tons of potential economically viable copper capacity globally that is completely stalled due to regulatory paralysis and social governance litigation.
So mechanically extracting the rock from the ground is a 2-decade nightmare. But getting the rock out is really only the first step. The middle of the supply chain, the processing layer, is where the friction becomes deeply geopolitical.
Because you cannot wire an AI data center with crushed rock, the raw ore must undergo a complex metallurgical journey. It is concentrated, then smelted in massive furnaces at extreme temperatures to remove iron and sulfur, creating what is known as blister copper.
Blister copper.
Right, and that blister copper is then cast into anodes and submerged in highly acidic electrolytic baths to be electro-refined into 99.99% pure copper cathode. This middle step, the smelting and refining, is subject to extreme geographic concentration.
And by geographic concentration, we are specifically looking at the dominance of China.
China currently controls approximately 12 million tons out of the 29 million tons of total global smelting capacity. Over the past 2 decades, while Western nations largely outsourced heavy, polluting industrial processes, China aggressively strategically built out its processing infrastructure, creating a massive centralized choke point.
And this centralization is creating a terrifying economic dynamic for Western mining operations. We are currently observing a total collapse in TCRCs. Let's explain what TCRCs are for the listener and why their collapse is a critical warning signal.
TCRCs stand for treatment and refining charges. These are the fees that smelters charge the mining companies to process their raw copper concentrate into usable refined metal.
Okay, so it's a processing fee.
Yes. But because China has built an immense surplus of smelting capacity and global mine output has entirely stagnated, like we discussed, the smelters are effectively starving for raw material. Their furnaces must run continuously, so there's intense cutthroat competition among smelters to secure raw concentrate.
Because if a furnace goes cold, it's a disaster.
Exactly. So this desperate competition has driven the TCRCs down to multi-year historic lows.
The smelters are essentially slashing their own revenue, just to keep the physical material moving through their furnaces.
It squeezes the operating margins of the smelters dangerously thin. But far more importantly, it creates a massive geopolitical vulnerability for Western economies. The United States and the European Union can draft ambitious industrial policies. They can subsidize EV battery plants and fund domestic AI infrastructure all day long.
But if they remain heavily reliant on imported refined copper cathode that was physically processed in a highly concentrated rival geopolitical hub,
then they are entirely exposed to sudden trade shocks, punitive tariffs, or strategic export controls. They don't control the middle of the pipe.
To visualize this massive systemic failure, I like to use an analogy. Imagine a vast reservoir of water, which represents the millions of tons of unmined copper trapped deep in the Earth's crust. On the other side of a mountain range, you have a sprawling, hyper-modern metropolis dying of thirst, representing the AI data centers, the electric vehicle fleets, and the expanding power grid.
Yes.
But the only physical pipe connecting the reservoir to the thirsty city is 17 miles long. The pipe is completely choked with bureaucratic concrete and regulatory friction. And the only water purification plant sitting in the middle of that 17-mile pipe is controlled by a strategic geopolitical rival.
That is a stark but mathematically accurate representation of the global copper supply chain right now. The fundamental vulnerability is that the global financial market refuses to look at the 17-mile pipe. The market only prices the water that is coming out of the tap today.
Which brings us to the final crucial mechanism of this deep dive. Understanding leading versus lagging indicators and tracking exactly where the smart capital is currently flowing to front-run the crisis.
Yes, the smart money is already moving.
To explore this, let's look at one final location. I want to take you far away from the hyperscale data centers and the rusted rail yards. We are traveling to the remote, mountainous wilderness of British Columbia, to a specific geological region known as the Golden Triangle.
The Golden Triangle. That region represents the absolute front lines of mineral exploration. It is where the initial friction of discovery actually occurs.
Picture a man named Marcus. He is a veteran exploration geologist working for a small, mid-tier exploration firm. He is sitting in a cramped, poorly insulated, wood-paneled trailer. It is so cold outside that his breath is visible in the morning air.
A very common scene in BC.
Through the window, he can hear the distinct, lonely, mechanical scream of a diamond drill rig biting hundreds of meters deep into the earth. It is a sound echoing in a remote valley that the global financial markets completely ignore.
They don't even know what's happening.
Right. And Marcus is looking at the screen of his satellite phone, checking the daily stock tickers for the major multinational copper producers. The commodity prices are relatively flat, showing minor daily fluctuations. Those are the lagging indicators.
Because lagging indicators reflect what occurred in the physical market yesterday, not the structural reality of what must happen tomorrow.
But in his cold, calloused hands, Marcus is holding a pure leading indicator. It is a shimmering, freshly extracted cylinder of solid rock. It is heavily mineralized with a specific copper-bearing ore known as chalcopyrite, which is characterized by its distinct brassy, metallic luster.
The raw potential.
He looks at the heavy rock in his hand, then he looks at the flat, unmoving ticker on his screen, and he feels a profound sense of isolation. Marcus lives his entire professional life in the gap, that massive 17-year delay between the physical discovery of an ore body and the final delivery of refined metal.
It's a long way.
He knows, with absolute, unyielding mathematical certainty, that by the time global capital flows down from the massive producers to his tiny freezing exploration camp, refined copper will be entirely out of reach for the average global consumer. He knows the broader market only reacts to lagging data, but the physical Earth dictates the leading data. He realizes that when the financial world finally shifts its attention to the dirt beneath his boots, the crisis will have already violently arrived.
And, you know, Marcus's isolation perfectly represents the fundamental illusion of stability in the current commodity market. If you analyze the headline data in early 2026, you will see that combined exchange stocks, the physical copper sitting idle in registered warehouses for the London Metal Exchange, the CME, and the Shanghai Futures Exchange, have climbed above 1.1 million tons.
To a casual macroeconomic observer or, a venture capitalist looking at a dashboard, 1.1 million tons of physical inventory look like a healthy, well-supplied, stable market.
It projects an illusion of stability, but it is entirely deceptive because it is a purely lagging metric. Inventory levels only communicate current, immediate physical availability. They reflect subdued macroeconomic factory orders in traditional legacy manufacturing sectors.
Right.
They provide absolutely zero data regarding the massive, unavoidable structural deficit approaching over the next decade.
So if the warehouse data is a deceptive lagging indicator, how do you mathematically spot the turn? How do massive, slow-moving commodity cycles actually shift?
Cycles turn based entirely on the physical sequencing of supply chains. It is a function of latency, how long it takes physical material to move through a constrained system. Let's trace the actual physical journey of a ton of copper for a second.
Walk us through it.
If an operation mines raw copper ore in North America, say up where Marcus is in British Columbia, it must be concentrated, loaded onto trucks, and travel roughly 250 kilometers over really tough mountainous terrain to a deep water port.
Okay.
If it is mined in the interior United States, it might travel 1,500 to 3,000 kilometers by rail across the continent.
And it still hasn't been refined into usable metal.
Exactly. The concentrate then endures a 15-day maritime voyage across the Pacific Ocean simply to hit that massive smelting bottleneck in Asia we talked about. This happens because while the United States currently produces roughly 1.1 million tons of mined copper, it is forced to import 890,000 tons of refined metal due to a severe lack of domestic processing infrastructure. Canada exports 450,000 tons of raw concentrate, the vast majority of it shipped directly to Asian smelters.
The physical material is constantly in motion, crossing entire oceans just to be chemically processed, and then shipped all the way back across the ocean to be installed in a data center.
That physical friction is the reality, and these structural delays, the maritime transit times, the processing queues of the smelters, and most importantly, the 17-year mine development timelines, these are the true leading indicators.
They are the warning lights.
Yes. When physical demand accelerates, as it is currently doing at an unprecedented rate with AI infrastructure, these systemic delays compound upon each other, creating a massive supply shock.
If the true leading indicators are flashing a severe warning, where is the intelligent capital actually moving? Let's trace the flow of money as the market begins to realize the trap.
Capital flow in heavy industry always follows a highly specific defensive sequence. When a price shock initially hits, capital aggressively concentrates in the massive, established Tier 1 producers. Companies operating massive legacy assets reap immediate margin expansion because they already have producing mines generating cash flow.
They're the safest bet at first.
But as the mathematical reality of the structural deficit sets in, these massive producers realize a terrifying truth. They cannot simply grow their output by mining more aggressively. They are constrained by declining ore grades and water scarcity. To grow, or even just to replace their depleting reserves, they are forced to acquire new assets.
So the capital is physically forced down the supply chain, moving from the giants down to the smaller players.
It flows from the major producers down to the mid-tier developers, and finally it trickles down to the junior exploration companies like the one Marcus works for in the Golden Triangle. However, there has been a massive fundamental shift in how this capital is currently being allocated. Institutional investors are exhibiting intense, ruthless capital discipline.
Define capital discipline in this context. What exactly are the investors demanding?
It means the financial market is completely shifting its focus away from high-risk, capital-intensive, multi-billion-dollar dreams that might take 20 years and endless litigation to permit. Investors are no longer willing to fund massive geological gambles in the middle of nowhere.
Because they can't afford the time.
Instead, they are aggressively hunting for execution-ready developers. They want advanced projects with low initial capital expenditures. They demand projects that have already secured their environmental permits. And crucially, they want projects located in established, safe infrastructure corridors.
Meaning places that already have roads.
Regions where the heavy haul roads, the deep water ports, and the high voltage power lines already physically exist.
They are paying a premium for absolute logistical certainty.
The market no longer cares purely about sheer commodity exposure. It cares exclusively about execution credibility. Having a verified geological report showing 1 billion tons of copper tracked deep in the ground is completely economically useless if you cannot physically permit it, extract it, process it, and deliver it to the market within the current demand cycle.
This entire deep dive maps an incredible physical journey that completely shatters the dominant macroeconomic narrative. We started in the hypermodern, supposedly invisible world of AI data centers. which are entirely dependent on thousands of tons of pure copper bus bars just to prevent massive electrical failure.
Yeah.
We traveled to the freezing, rusted rail yards of the industrial Midwest, where the ambitious timelines of the green transition are bogged down by 1950s transport infrastructure and the physical weight of cathode plates.
And then into the ground.
We explored the deep, unforgiving geological realities of declining ore grades, the massive energy penalties of desert desalination, and the crippling 17-year logistical lag required to build a single new mine. We have demonstrated that the so-called weightless economy is a complete illusion. It is entirely, desperately dependent on the heaviest, most unyielding, most physically demanding industries on the planet.
The disconnect between the digital narrative and the physical reality just cannot be sustained. The abstract narrative of infinite growth must eventually, inevitably bow to the hard math of physical necessity.
The ultimate boundary to the age of AI will not be determined by the ingenuity of software engineers, the theoretical limits of silicon architecture, or the billions of dollars allocated by venture capitalists. It will be decided by the sheer, unavoidable physics of pulling an ancient red metal from the dirt. The digital future is entirely at the mercy of the physical earth.